Dunlap. Oh, nice. And he's got 2 dogs, which is very exciting.
Yeah.
So we're starting a little bit late today. So let's maybe keep the in-talk questions to a little bit of a minimum, so we can give Josh the opportunity to get through the talk he made. And if you do ask a question, I think it'd be nice to say your name and then ask the question. So Josh, is that all good?
Yeah, works for me.
Cool.
All right, thanks so much for the intro. I'm excited to be here. So I've only, it's good you mentioned the dogs. It's actually the first time I came to Kitchener-Waterloo was actually to adopt one of them. So we actually had to drive out here. So these are the 2 of them. So the top one over here, this is Kumo. He's the old one actually. We got him in graduate school back it's almost 8 years ago now. And then this one down here is the one that we adopted so originally from Costa Rica, but from an adoption agency based in like Kitchener-Waterloo where their foster was. So she's Aki. So that's the connection there. So I'm very happy to be back. And as Alexa mentioned, there are a lot of things that are 2s in this talk. So I have sort of a cross deployment in statistics and also in astronomy. And that also means the talk is going to sort of have like 2 focuses because I really love like fitting things more or less. So I love data sets and just working with data. And so what that's meant is that I sort of have been all over the place in terms of what I do. Alexa and I sort of met when I was doing doing more galaxy stuff. And I have like a galaxies oriented talk, but I thought I could chat a little bit more about some of the stuff I did for my PhD thesis and I've been working on more recently, which is more related to stars in the Milky Way. So I'll just sort of start out by sort of asking the basic question about like, what is the Milky Way and why I think it's cool. Part of the reason for that is that I thought JWST was really cool when I was in graduate school until it didn't launch on time. Then I had to find something else I thought was very cool so I could graduate. Or else I'd be working in simulations. And right around this time, Gaia DR2 came out. And one of my PhD advisors, Charlie Conroy, had like a little hack session. And I was working on a lot of photometric redshifts in cosmology at the time. And I think Ben Johnson, who's one of the postdocs in the group, made some offhand comments about how I could probably, fit stars with the same approach, except the parameters would actually mean something. And it was like, ha, ha, ha. We all had a good laugh. And then I went home and I was like, I think he's right. And then that turned into my PhD thesis. So nice story about how I randomly switched fields. And it's been fun ever since. This is my favorite picture of the Milky Way, which is the one taken from Gaia. And I think what I love about this just shows all the stuff you can learn by looking at your own galaxy. In particular, you see tons of structure, you see nearby stuff. And most importantly, you see lots and lots of stars. And stars are great because stars are the building blocks for galaxies and ultimately the things that we can learn a lot about when it comes to studying galaxy evolution. And so the basic idea that I focus on is trying to use the Milky Way as kind of this special laboratory, right? Sample size 1 that gives us insight into how other galaxies might work, right? We look at all these cool pictures of other galaxies. Here are the nice standard pretty pictures taken from Hubble. Soon, we'll replace all of these as JWST images. And like we want to ask where our galaxy fits in, right? And of course, we can't get the picture on the right, or at least getting the picture on the right is very, very hard because we're inside the galaxy. So we have this problem where we're trying to sort of map out things, right, from the inside out. And we are stuck making these artist conceptions. Very good artist conceptions. I'll sort of show exactly the data that was used to make this one. But fundamentally, they're artist conceptions. And so if you want to understand this microphysics and its connection to macrophysics, we need to first come up with a way of figuring out what the Milky Way is actually doing, how it assembled. And the second part, which I'm not going to talk about today, is then putting it in context about figuring out what parts of the Milky Way can we really extrapolate from and figure out like where it fits in with things, like in terms of other similar galaxies, and what stuff is just kind of unique to its own assembly, right? It's like trying to ask a question about how many of us got to be here today. There are some ways in which our stories are, share other things in common with other people in the room, and many ways in which they're different. And trying to figure out which ones of those we can learn from and what lessons we can draw is a lot of what I focus on. So that's where we are, at least according to this artist conception. And so the problem, of course, is that I'm going to talk about today is all about galactic structure, figuring out how do we get that picture on the right. So we have this model, and we're here, right? And what we see when we look out at the sky, in a particular cone is something like this, is this 2D projection. if we take 2D projections over time, we can measure some, types of proper motion, or maybe we can get some radial velocities to some stars. I'm at Waterloo, and I'm very excited about things like DESI and SDSS5. And so this is sort of what we're looking at. And we have this inference problem where we need to go from, the data to the model in this particular case. So this talk is going to be broken up into 5 parts. I can spend more or less time in various parts depending on how interested people seem to be. And then like the sort of some cool stuff that I'm doing more recently, we'll sort of go into part 5. But the idea is to just give a nice preview as to what types of problems sort of are involved in this. And then some results that come from what I like to think of as just data-driven discovery, which is developing lots of cool statistical methods, which is what I love doing, and then working with other domain experts, applying it to large data sets, and then you just find cool stuff, which is great because we have lots of big data sets now. So I'll start with history, and then we'll sort of go through these other parts and how exactly they fit in, and hopefully people will find it fun. So the history, I think, is really fun because we've been trying to map the Milky Way for a long time. And this is the first map made by Herschel in 1781, published in 1785. And Herschel, of course, right, big named and lots of great stuff all over the place. And this is his map of the Milky Way. And now you might look at this and you might say, cool, okay, what's going on here? Every dot here is a star. And if you're looking at sort of these types of things, you might be like, all right, this is kind of a weird map. As always, the sun's in the center. But there's actually a lot of things about this plot, this first map that actually Herschel gets right. He notices, for example, that the galaxy is asymmetric on both sides, right? It's sort of longer on one end, shorter on the other, right? And you also get this chunk that's cut out here, which of course is towards the galactic center. You also see that there are more stars in some regions, like this is very dense, versus over here where you get kind of this filamentary structure, it becomes a lot less dense. Now the question is, how exactly did Herschel construct this map? The main idea is sort of the fundamental problems with galactic structure is that he did it using 2 approaches, right? So you go out, you look at a given patch of sky. Let's just zoom into a given region. So we have this here, and you see lots of stuff. And the question is, what do you do? The first is you make 2 assumptions, right? The first is that you have a bunch of dots, and you say, let's just assume that stars are the same. So that way you can do very simple distance estimates, or at least relative distance estimates based on how bright the star is. Seems reasonable. People have been doing this for a long time. To first order, right, it's probably not the worst assumption. So there you go. You can just write down the formula. Everyone gets distance modulus, and then boom, we're happy. The second is that there's no intervening material. Herschel, of course, becomes the person who does a lot of stuff with dust. But the idea is that, when you look at density, essentially what you observe is sort of proportional to the truth, right? So in regions where you see sort of these dark lanes or bright lanes, that's sort of background stuff, but actually the density of stars you see in various parts of the sky, that's actually proportional to the true 3D space density. Now, both of those assumptions turn out to be wrong, and they affect sort of the inference in different ways. But this is kind of like a very good starting off point, in my opinion, right? Like it's a great place to start. The concepts are here. And this is, Herschel has innovated on this, hundreds of years ago. So if we go to the first one, right, what does this do? So of course, right, like we want to measure distances to things. We gotta, go stick to the standard HR diagram. So this is sort of like the Gaia version. I love this plot. Every time I look at it, I just think it's like the coolest thing ever. So this is the CMD or Hertzsprung-Russell diagram. You have brightness, or magnitude on the y-axis, color on the x-axis. You get these different populations. The color is density here, except at the edges where they become individual points. And of course, the key idea, right, is that this isn't, stars are not the same. They follow a particular sequence. This sequence turns out to be an evolutionary sequence, right? And this plot, because it's been derived. Yes.
What's your name?
May I ask? So can I ask, is this all the stars of Gaia series, or is it?
No. So this is a small subsample with very, very high signal-to-noise parallaxes, and that's so that they can get sort of put them all at the same absolute magnitude. So I'm trying to remember. I think for this plot, the cut might be like 20, 20 or 10 for the signal-to-noise. So it's not anywhere close to all the stars it sees.
It's everything above signal-to-noise of 20 or something.
Yeah, there's some other quality cuts, but in general, this is yeah, they've done some cuts to make sure that they really trust the distances here. Yeah. So like these populations are real, and this intervening one, for instance, like all these points, these are also real. These, for example, are like white dwarf main sequence, like white dwarf M dwarf binaries, for example. So like this isn't just random noise. Same with like lots of these stars, like there are a bunch of blue stragglers and other types of things up here as well. So it's great. This data is just insane. And this has all been derived right using parallaxes. And so the idea is that if you see an apparent magnitude, this just adds a small, hiccup to the idea. You can just draw a line, right? And then you say, okay, here's the observed color. There's the observed magnitude. If I know what the true population of stars is, I don't know anything else. It's just, that's my probability of where the distance is. Nice and easy, right? Condition on the color. Here's what the absolute magnitude has to be. You get a distance modulus, and that allows you to convert immediately from an observation into an estimate for the distance. So that sort of solves that one problem. Now, the second issue, which makes things a little harder, is the dust problem. Dust is great. So I love dust. Also on my PhD advisor, Doug Finkbeiner, worked on dust, so I feel like I'm obligated to like dust. But dust is awesome just in general, mainly because it scatters a lot of light, and that can be a very bad thing, but it also means it's a really good thing, because you can actually use it as a very effective tracer because of how it affects starlight. The fact that it sort of extinguishes and reddens the material. So here's like one of the standard maps I love showing. This is in galactic coordinates, so longitude on the y-axis, longitude on the x-axis, latitude on the y-axis. The Milky Way plane sort of cuts through the center. You might see a lot of echoes in this map versus what you saw with the Gaia map, right? All these dark regions and lanes shows tons of complex intervening dust structure, and the color is proportional to the overall extinction from dust. So with this, right, dust has an impact on two impacts. The first is extinction. So dust just is blocking light, so it makes everything fainter. This is often called like a gray component, but in general, it just means if you have some intervening dust, everything kind of gets fainter by some amount. The second thing is that it also does it in a wavelength dependent way. So it tends to be more efficient at blocking shorter wavelengths, less efficient at blocking longer wavelengths as you sort of get wavelengths larger than the size of a typical dust grain. So that means, for lots of things in the visible, if you look at a dust cloud, you see that you're missing a lot of stars. When you look at the infrared, you actually can see sort of through it. And in particular, what I love about this plot is you can actually see the reddening effect kick in like really clearly on the edge of the cloud. For both of these, it sort of gets immediately, like you can see as you get closer, the stars just get redder. And that's sort of this intervening effect where before all the light gets completely blocked, you're actually blocking preferentially the bluer wavelengths. So it's great. This picture is awesome. Here's what that curve looks like as a function of wavelength. So the axes here are a little weird. The y-axis is 1 over wavelength to kind of emphasize the ultraviolet dependence. So I've sort of drawn like indicating which direction you're going for each one because I found this very counterintuitive. The y-axis is kind of this normalized extinction, characterized by these color excess numbers that are used a lot. But key idea is that upper means more extinction, lower means less. And you can get negative numbers because you have this arbitrary sort of 0 point. It's very difficult to measure like exactly the absolute amount of light that dust extinguishes. So people often talk about things in terms of relative attenuation. But the key idea is that this depends a lot versus where you are in the Milky Way. You get the shape that changes. You also can have this gray component. This normalization can also change, and there's some uncertainty in setting like the overall scale of this. And this depends a lot on internal properties of dust grain composition. So we can't even assume that dust is the same everywhere. So we don't even know what the total impact this has on our observations some of the time. So we have to make a lot of assumptions. So this just shows how much you can vary. By the way, this is sort of foundational work by Fitzpatrick and Massa. You can just see these are just overplotting like hundreds of dust curves, and follow-up work by Fitzpatrick has sort of clarified that this can vary a lot in the galaxy because dust varies a lot in the galaxy. Now that's a lot about dust. What does this do, right? What it means is that the observed color we see, we were conditioning on the observed color and assumed it was the intrinsic color. And most of these stars are all so close by, and in general have been selected so that we don't think there's a lot of foreground dust. So this we can think of as an intrinsic color distribution for stars based on real data. Once we sort of say that that's not true anymore, the idea is that we can't just say that it's this, right? Now we have this gigantic region of uncertainty, because the intrinsic color could be a huge range. It could be much more intrinsically blue, and just we happen to observe it being red because there's a lot of foreground dust, right? That could be fainter and redder in that sense. So let's look at two examples here. So I'll look at what I call a low mass solution and a high mass solution, sort of a redder and bluer option here. The low mass solution has less rending and it's closer. In other words, if we observe a red star, that's because it's a nearby faint M dwarf or something like this. So in that case, nothing fancy. Or it could be much further away. You could be thinking something like, a G dwarf, or K dwarf. And in that case, now it's brighter, but there's more foreground dust. And so you have to put the object further away and add more foreground dust to sort of get the exact same rough colors that you observe. And you might notice as well that this other curve here also intersects this upper branch, the giant branch. And so you also get this age degeneracy, because stars can have the same temperature when they're on the main sequence or in the giant phase, but extremely different luminosities because of the different sizes. And so that's this age degeneracy about whether you're looking at like a K dwarf or K giant type of thing. And that fundamentally can lead to bimodal distance estimates, where either the object is very close by, or you have to put it like 10 times further away to sort of get the same overall observed flux contribution and same colors. So this can sometimes cause some very weird behavior too, depending on exactly the observed possible intrinsic color. So what does this look like in the end? Like, what's the result? So the result is something like this. So I just want to break down what this plot is showing. These are a bunch of different cutouts specifically towards a particular star-forming region. The region, I believe, is Orion. Each of these cutouts on the y-axis, this is looking at attenuation, and the x-axis is looking at distance. I think it's in distance modulus. This is, I think, is in units of AV. The shaded region is the actual posterior probability. I'll describe the algorithm we use to get these in a second. You might notice a small red dot if we sort of zoom in really closely, like right here or right here. That's like the most likely solution. The MAP usually is what it's called for the particular star. But the key thing is just that these are gross, Like if you look at this star, for instance, right, you get these really long curving degeneracies that sort of go up. This one has 2 solutions, you'll notice. This one has like 3. You notice even there's like this extra one over here. So it's not pretty. And this is like very typical for lots of stars. Yes.
So what data are you using for this?
So excellent question. So for this one, we're using photometric data from Pan-STARRS 2MASS and as well as Gaia parallaxes.
Okay.
Yeah, so primarily based on photometry and colors.
So you do have parallaxes then?
We do have parallaxes for lots of these stars. Not always, though. We don't require them, but they do help. Yeah. But the idea is that this is actually very typical for what things you get out, especially for stars that are further away, where the parallax is often much noisier and not nearly as much of a strong distance constraint. So the issue here is that we have these large uncertainties, complex degeneracies, and these multimodal solutions. So if we want to do this on a widespread case, which is what I'm always interested in, to large data sets, you need larger sample sizes because you have a lot of noise, right? So you need many stars to sort of average down over this. You need very robust inference because you have multiple solutions. You don't want to miss one, or you might really bias yourself. And you need a lot of computing power because it's non-trivial to sort of do this. So this is one reason why in the past, astronomers said, this is hard. Why can't we do something easier? Let's make it hard on the observing side, but let's make it much easier on the statistics side. And so in the past, a lot of galactic mapping has used masers. Now masers are great because you get these, giant like microwave laser systems. They come from these star-forming regions through like stimulated emission. So here, and they tend to be in the most dense regions. So this is a star-forming region. The maser is in this really like center dark point where we don't even see like any stuff at all. But here's where we get a maser. And because this emission's coming out, in the radio, that means you can get interferometric parallaxes to them. And those are very good. They just take a long time. But the idea is that, rather than working on a lot of very noisy observations, you can take one very, very good observation. It just takes a lot of time. You just front load a lot of that effort so you can have easier data later. So This is, by the way, the exact maser data. I'm just overlaying it over the plot of the actual Milky Way. So if you zoom in, I've sort of overlaid these tracks taken from a paper from Reed et al., who's done most of the work as part of the vessel survey on this program. So you can see sort of these little dots here if you zoom in. And actually, this is the same data that's used to trace out the spiral arms and map out the Milky Way to make this artist impression. There's some other things that are worked in as well, but you can actually take both the plots from the paper and the artist impression, like overlay them on top of each other and see that they match up. So the issue, of course, right, is that if you look at this particular plot, right, like why not keep using masers? One is that ultimately masers are just rare and they're very hard to get observations to. They require very intensive observing campaigns to get very good parallaxes. But what's cheap, what we do a lot, is imaging surveys, right? Stars are everywhere. We get imaging surveys for everything because people love surveys. I love surveys. And we also now are in a very different regime than before. We have lots of computing power. In many cases, it's actually cheaper to request millions of CPU hours than it is to get like a night on a telescope. So given that trade-off, right, it just makes sense cost-wise, statistics-wise, like just numbers, to be thinking about using stars instead of trying to use masers to solve some of this problem. So that's the problem formulation. So now I want to go into talking a little bit about how we actually do this. And I don't want to go into a ton of detail on the stats. People can ask me a lot about it later, but I had a lot of fun with this because I love working on stats problems. So the main requirements, as a reminder, is we need to be able to infer probability distributions or uncertainties that look like this, right? Disgusting. So we need one that can characterize these multimodal complex uncertainties. We also need one that can be very fast. So we're thinking like seconds per object. Yes.
Lisa, just to be clear, are you trying to get accurate distances to each individual star or
Yes.
like a region?
Individual stars. Yes, we will be getting distances to individual stars we can then use to get distances to regions later. Yeah, but this is sort of the bedrock that we want to use to do downstream analysis. Good question. So the challenge here is sort of that we have this difficult thing. And so the approach that we're going to take is a Bayesian one because we want to have all these complex uncertainties. And I will break this into two problems. One is that I'm going to talk about the star itself, which is like you can take a star, just move it around the galaxy, it's the same star. And then also where it is in the galaxy, right? So these are things like distance and dust. Turns out these have different effects on the model. And so if you break up the problem into these two parts, you actually can solve this problem much more efficiently. So this is what the model looks like. This is just writing down sort of some notation here. And I just want to highlight kind of what these things are. So the intrinsic parameters I'm calling sort of like theta, and then the extrinsic parameters I'm calling phi, and the observed data is like the magnitudes and the parallax, which are m and sort of this var var w. I've never quite figured out the name. So we have one point that comes from the actual colors, the actual images, another that comes from the parallax, and then a final one is what I call the galactic model prior, which is where what we think the galaxy looks like, broadly speaking. Yes.
That's called curly pie. Is that right?
I think you're right. I think that is curly pie.
Is it really just curly pie? All right, excellent. Curly pie.
Very old people know that, and I had some very old people.
Yeah, so the idea is we have these three components. I just want to go through sort of writing down how we fix each of these. Since it turns out that some of these are easier to work with than others. So the images are straightforward. The idea is that we have a model that looks essentially like this. So it's a linear model. And the idea is that the observed magnitude is just the intrinsic magnitude of the star, which depends on the actual stellar parameters, this theta, coupled with a set of coefficients that are coupled with the extrinsic parameters plus some noise. And again, these extrinsic parameters are things related to distance and dust. So if you adjust the distance modulus, for instance, that just rescales the magnitude up and down. And if we add dust, and we assume that it sort of affects these things in sort of as a rending vector to first order, and even to second order, we can assume that it has like a linear impact on the observed magnitude. So we can sort of write this down, and it turns out that you can solve sort of a linear system very easily, which helps. The parallaxes essentially are normally distributed. So it's just 1 over the distance plus some extra noise. And the Gaia team has gone to great work and shown very convincingly that the data are distributed extremely normally up to like 4 sigma, which is fantastic. There are some like systematic biases, but overall, the statistical uncertainties that the team produces are quite robust, which is great. And then finally, we have like our galactic model. So our prior assumes kind of 3 general components. So we call them thin disk, thick disk, and halo, but really we just have 2 disk densities and then a halo density model. And those are taken from like a big review paper from like Glenn Hawthorne and Gerhardt with some small tweaks. But the idea is that we just broadly have 3 density components, and that means depending on where in the sky we're looking, you know, if our line of sight, say if we're here and we have a line of sight, so we're looking up versus looking like through the disk or out of the disk, we're going to have a different prior for sort of how many stars we expect to see at a given location, and also what the metallicity distribution for those stars might be as well. If we're looking sort of something out in the halo, we probably expect to see stars that are a little bit more metal poor than stars that are in the disk, for instance. Again, yes. We do not have any prior for clusters having different properties than stars. This is primarily looking at field stars. I have a different framework for actually fitting clusters, which I would be happy to chat about. But yeah, we have not considered those here. Yes.
Just a point, but the Gaia parallaxes aren't nearly as good in clusters, right? Because it's going to take a few more data releases on Gaia to sort out the crowded field. So
yeah, that's right. That's right. They're better on the edges and less good in the center. Yep, exactly. They also have strong color dependencies in clusters too. So that's the model. So then the thing is, we have the model, we want to estimate what the distribution looks like. So we want to get the blue thing. So we got to find some way to sample from the posterior because we can't really estimate it directly. Now, typically we would run something like a Markov chain Monte Carlo algorithm, but these are not very good here. So you sort of start from some distribution, you random walk around, and then based on sort of where you are, how much time you spend there, typically MCMC returns to you some like set of positions that you can take as being representative of the uncertainties. This doesn't work for us because we need to go to actually move between these different modes. So we need to somehow jump from like here to here and possibly to here. And there might not be like a bridge connecting those two. They might be separated. So one solution is something called nested sampling. This is something I did for as part of my thesis. It's what I've become sort of most known for. Is a code called Dynasty, which people use, and I'm very grateful. And unfortunately, here it turns out that all the effort I put into this code doesn't really help us with this problem because it's too slow. In other words, generic problem for a very specified bespoke solution, sometimes doesn't work. It's the same with lots of people in coffee, right? Everyone's like, oh, sure, I can always go get a coffee, but then you have your favorite, barista at your favorite coffee shop or something, especially if you're in Seattle. So solution 2, which is what I did, was I threw the kitchen sink at it. So I said, all right, let's just try and do everything statistically possible to solve this problem and see what we can come up with. And so here's what we came up with. So we broke this breakdown I mentioned earlier actually comes back. Because it turns out that the stellar types actually matter a lot. So we have this regression problem. It turns out that's a solves problem. So assuming that we knew what the star was, we can immediately solve for what the posteriors are on all of these extrinsic parameters. So distance and then dust in particular. And actually the model we have is able to, for the first time, incorporate variation in the reddening curve as well. So we actually are able to solve for sort of both components, both the overall extinction measured by AV and then also the shape measured by RV at the same time. So that's great. We just solve immediately. Everything turns out to be well behaved. Life is good. So, check 1. Then the problem is we don't know what the star is. So we got to figure out what to do there. So luckily, for our purposes, stars are not too bad. So there's usually less than 4 parameters we can say roughly characterizes most star systems. Essentially initial metallicity, initial mass, and age, ish. Obviously stars are very hard, but for our purposes, that's usually enough. You might say maybe some dependency on like alpha or rotation rates, that could be like additional parameter. But as long as we're sort of like 4 or less, it turns out you can actually just brute force this problem. It's very fast. You can vectorize the whole thing, parallelize it across lots of stuff, works great. So you just compute all of this over a grid, a gigantic grid you can pre-compute, and life is good. Then you have this final part, which is we have priors on stuff. We have a parallax, which we haven't talked about, And then also we have this galactic prior. And so what we do is this is so far just solved for all this likelihood stuff just based on the image. And now we get to use something called importance sampling to kind of retweak our guess. So essentially we start with like this green curve and we're going to sort of tweak it so it looks a little bit more like the purple curve. This usually works as long as the green curve and the purple curve like roughly overlap. In this case, most of the time they do. So we do this strategy, and then that allows us to finally get these blue curves. So this is what we're actually using to get all of these particular like plots at the end. Yes.
This is Alexa, just for the people on Zoom. I'm just curious because you separated the parallax uncertainties from the photometry magnitude uncertainties.
Yes.
And so your imaging is not Gaia imaging, or like are there covariate? Are those uncertainties actually the same uncertainties?
Great question. So in most of these cases, we have not used Gaia photometry to do the fit. We've used other ground-based photometry or space-based photometry. In the future, we're hoping to use Gaia photometry, and then we would consider the full covariances when doing the solution. But yes, for now, we've assumed that they're independent because they've been derived through independent data sets. Okay. Yeah,
Thank you.
great question. So the code's called Brutus. It's been publicly available for a while, but as with many things, like actually getting my PhD published has turned out to mostly be difficult because it's my fault, Taylor Swift song, right? Who's the villain? It's me. But it's all online. We're in the process of like going through revisions now. It's open source on GitHub. You can use it. It includes some grids, some built-in plotting utilities, so you can actually look at things like posterior predictives to get uncertainties from your results. And then you can use it, and there's like some notebooks showing how. But it's there, just so everyone knows. I'm a big believer in code, so usually if I develop a tool, it's going to be available on GitHub somewhere, even if it's not super well documented. I'm always happy to answer questions about it. Okay.
I just did.
Yes.
Just quick. So the brute force is faster than Dynasty here because you separated out
Yes.
part of the problem that you could solve analytically.
Exactly. So rather than having to solve for like 7 or additional parameters all at once using like a big sampling method, you have to query the models on the fly. Because we can pre-compute some of these on a grid, and then the solutions for the other ones are analytic, we can actually dramatically speed up the problem. Yeah. So, but the punchline is that this means that most of the runtimes end up being on the order of a few seconds. If we have very good parallaxes, the runtimes are fractions of a second, since that cuts out almost all the parameter space immediately, and we can do lots of speed ups. If we don't, then things can take longer. We currently have a project where we're trying to do mapping in the plane where we have like very few bands and no parallaxes. And in that case, we're often looking at, like 20 seconds per star, which is, not what we want, but what we can do. So I'll sort of show like 2 fun science examples. I don't want to take too long because I want to make sure that we're all wrapped up by like 12:30, right? Is that the pizza time? Because everyone wants pizza. And then I'll show some like fun stuff as well. So the first thing we've been looking at is how do we use all this data to do galactic mapping? And the first thing is we want to look at some spiral structure and just local star formation. So idea is that, we are looking at young stars. We want to trace spiral structure, galactic structure. We want to look at gas. We want to look at young star formation. So, and dust traces all these pretty well. So if we can map out these star forming regions, we can sort of see what's going on for lots of these things, because that's where masers are in these places. So the idea here is we can now sort of leverage exactly that. We have a bunch of noisy observations. We're looking at sort of this, effect from extinction and reddening. Before, this was a big drawback, right? Oh my gosh, every individual star, the distances are so uncertain. You have a lot of stars. You start to pull information together. This is great. You can actually use this to map out 3D dust. As long as you can see some stars, you can get a good view of this. So you can't have too much dust. So what can we do here? So this is a project that I started with Catherine Zucker while she was at Harvard. She's now at Space Telescope as a postdoc there. And the idea was if you look at a cutout like this is Perseus, and we just take a little pencil beam and you ask, what does a cloud, a star forming cloud look like? And we split up like this. Here's what you get. Essentially, there's some foreground dust. This is cumulative dust, essentially, as a function of distance modulus. You have some foreground with some scatter, because stars will be at little different places and have little different local changes in dust density. Then you get the cloud, which is very thin. We're assuming it's infinitesimally thin, which is not the best, but it's good enough, it turns out. And then afterwards, you don't have a lot of dust. So most of the dust is concentrated behind the cloud, is at the cloud location. So we're fitting a step function, and we expect to see this huge jump. All the actual uncertainties are going to be these, blobs here. This is like one of the actual posteriors we get, and we want to integrate this model over all the different stars that we see. So the idea is, imagine overplotting all the different posteriors here. We're going to fit this joint model, and we're going to figure out ways to make it work. We also account for a scatter. That's the cloud. That's where the stars are. And we also account for intrinsic scatter, plus actually outliers, just in case. I was talking with Alexa earlier about robustness. We want to make sure our model is not affected by the fact that we know sometimes we're going to get the stars wrong because our models aren't the best or because they're just weird. So we also have parallax measurements, and they do help a lot. So in this case, this is what I was showing you before for lots of these stars. This is before Gaia. We look at after Gaia, so we conclude the parallax, you get this. So you'll see there are two different types of behaviors that show up here. One is that the parallax can really narrow down a solution. So if you look at, for example, like 1, you can see this happen exactly, right? So it just really narrows down the solution because the parallax gives you a precise distance. Sometimes, though, the parallax doesn't actually give you a very precise distance, but it does rule out certain types of distances, right? If you have a very small parallax, then likely your object is far away. It can't be close. And so you do see evidence of this, for example, for a few of the stars, like this one, where it actually prefers it to be at this sort of larger distance instead of the smaller distance once you have a parallax. But it's not actually able to tell you what the distance is. It's just able to prefer a class of solutions. So we see all sorts of behavior. And again, not every star has a parallax measurement associated with it. So if we don't, we sort of default back to what we see here. Okay, so here's what we get. Now, actually, we do use Dynasty to sample the posterior. So I've come back to the code. It actually turned out to be useful. Hooray. Here's what we get, like a plot that we look like. So this is the actual fit. The scatter is sort of shown here by like the upper lower bound of like this blue line. The posteriors are all these like random blobs. You can see they really merge together later. And the 1D marginalized posterior distribution for the distance is sort of shown here on the top, just to try and compact as much information as possible into one plot. So what's fun here is that you can actually see there are two potential distance solutions. And that's because we don't know whether the jump starts here or the jump starts here, which makes sense. We only have like 5 stars, before like things really elevate. So it makes sense that we actually don't know whether the cloud's, sort of closer or further away. So not too surprising. In general, though, lots of posteriors look better than this. And if we do a comparison of all the nearby clouds that we actually can measure masers and these distances for, we get really nice agreement. I mean, like, it's not usually the case where you just fit like a one-to-one line and it turns out that it's actually like the best fit line, right? So we fit this line, we incorporate all the uncertainties here. You can see some of the scatter we estimate, and we actually get very, very good agreement with the high resolution masers. So this gives us a lot of confidence that out to even a few kiloparsecs, our model, which again, is not that detailed, right? We just are fitting a step function. Actually is doing okay. It's actually doing all right. So one thing I love about this, Catherine really got me on board with this because she worked a lot with Alyssa Goodman and got me really into interactive plots. So I just want to show you guys what some of these look like, because this is, I think, the coolest part of the talk. So this is an interactive figure. You can go online to sort of see what this looks like. So this is one where you can click on any cloud and it will pull up a plot of that cloud. I love Cepheus because you actually see this type of detailed structure. So on the left, if you go over, it shows you the actual location and the rendering value. You go on the right, you can see all the pixels where we've sort of done these pencil beams. And if you mouse over them, it will show you what all the data looks like. So you don't have to believe us. You can actually go and see every single fit we've done and judge for yourself whether like that looks okay or not. And this I love because it shows also the limits of our model. So up here, there's sort of one foreground cloud at a certain distance. But when you go down to this other part of Cepheus, you see that it's green because it has a different distance solution. And you can see what's happening is we have this one cloud over here and this second background cloud, and it's fitting the height of this cloud and the rough distance. But it's clearly like not, able to capture all the structure there. But it is able to determine that like there is actually, a foreground versus a background here. And you can sort of guess what the overall like width of the cloud is based on like, looking at this. So the distances are way underestimated here, but like overall, it gets the typical thing correct. So Anyway, I love this stuff. So it's nice and fun. Okay. So I'll also show you the other thing that we've done with this. So we've also done some other stuff with galactic structure. This is sort of showing all the results we get from the fits as these little like blue points. The background points here, this is all like this black grayscale is from 3D dust mapping. That's work that Greg Green has done. He's at MPIA now. And you can see overall, we get really good agreement between these two approaches, between these individual regions, using like all the stars to do general non-parametric 3D dust mapping. In particular, what was fun about this is that we just looked and found like this gigantic structure that doesn't really align with the line of sight, which is where you expect all the systematics to be, like, in this sort of region or in a certain direction, like here. And when we actually modeled it up, we got this really like crazy undulating wave, which again, we didn't necessarily select. And when we went and targeted specific regions that don't have named dust features, they actually agree really well with this. So this was called like the Radcliffe wave. And in general, the argument that we've been making is that this is actually one of these two superstructures that appears to contain most of the star formation around the local bubble. The other one's sort of this other sort of split over here. And this idea of like a ring of star formation around us doesn't appear to actually align with the kinematics and other properties of data here. So we really are seeing kind of these two structures cross each other and not sort of seeing like a little ring of star formation. We've also revisited things about the local bubble as well. So if you zoom in on kind of, the central region, Catherine's also used additional velocity data and things to actually estimate ages for that. And there's like a nice second nature paper that's come out of all this work that she's led. So we've gotten estimates for ages of this and sort of supernova injection rates to sort of get the overall like energy injection for this. But it's fun. And this was all essentially just based on the fact that we now have distances to all these regions, accurate to like a 5% level. So that was, a serendipitous discovery on both ends, which we were pretty excited about. Mapping the galaxy at large, I'll be pretty quick on, because really the idea is that if we want to just look at all the stars, how can we do that? I think the real thing is that, I wanted to do this as part of my thesis. So I did a proof of concept with 170 million stars, with the goal, hopefully very soon, of doing all 1+ billion stars in Gaia. And we call this Augustus because the first thing that comes after Brutus, and so the idea was that we sort of cut out the plane because we can't fit all the stars here, and we don't have stars in the southern region because we're using pan stars, and we also have a magnitude cut because we can't do things that are too faint. But in general, we get like a very nice sample, and here's sort of the number density distribution, and we get very, very good agreement with lots of other distances that have been derived in literature. So these, for example, are ones taken from Andrews et al., used a different approach called Star Horse, but similar idea. And then this is from Baylor Jones from the most recent Gaia EDR3 release. And you can see in general, we get very, very good agreement with 1-to-1 with our distances with all these other approaches. But what I think is fun, and I'll just sort of skip ahead to this, is that we've done some really nice visualizations of trying to see what this data actually looks like. And that is here, which is a public website that everyone can access. So this is trying to look at the actual bulk motion using proper motions from Gaia, along with our 3D distances in various slices around the galaxy based on sort of maps of wind speed and ocean currents on the Earth. So if you click on a given region, it's interactive. You can actually see the direction, the location, the speed of all these things. You can change the inputs if you want to look at something like density. So you can actually see, for example, we get very coherent motion, even though we're losing a lot of stars, indicating that the dust is not actually affecting lots of the kinematics. This is our particular distance slice that I like. You can also change the projection because I love actually looking at this on a sphere. And you might notice, for instance, if you sort of zoom down over here, there's a lot of coherent motion that seems to be in this region. And if you sort of zoom out a little bit to look at a slightly larger distance spin, maybe switch to velocity, you actually see this overall feature. And that is the Sagittarius stream, which just shows up in our data very cleanly. So Sagittarius dwarf galaxy is merging in. We get really nice stuff. We also detect flaring in the outer set of the disk. And you can also see things like clusters, which show up as like little dots, usually at high latitude. So let me see if there's you can see a couple of these show up very clearly here. So overall, we actually are able to recover a lot of stuff, which is great.
like here, so these velocities are in what frame? Are they with respect to the sun or?
There with respect to the sun, yes.
Okay.
Yeah, everything's been proper motion converted to tangential velocity based on
The
distance.
center of the galaxy here.
Yeah, not relative to the center of the galaxy now.
Now is probably a good time to wrap up and open
Yep.
for some questions before pizza.
Exactly. So that's essentially most of the fun stuff. So I'll skip over the rest of these and just say that, looking ahead, really the thing that I'm really excited about, and that lots of people in the group, sort of research group that I'm assembling at U of T is really trying to do is connecting lots of this galactic structure with various parts of evolution and hemodynamics. And so I've been working with, a couple students, Arya Batil, who's been supervised by Gwen and Joe at U of T, who's done astroseismology, and Phil Van Lane, who's a first-year graduate student, who's been working on a gyrochronology project with me, using some machine learning to get stellar ages from rotation. A bunch of students working on chemical tagging, including Alex, who actually, people are interested, has been doing work on Gaia XP data to try and use DR3 to derive some chemical distributions. Some work on the stellar halo, along with grad student Maraid, and then also an undergrad Grace, who's actually in computer science and worked with us as part of a summer program. And then some 3D dust mapping work, and then also a fun side project with Alicia, who's actually been working on using simulations like Illustris and Eagle to try and contextualize our galaxy a bit better. So with that, I'm essentially happy to sort of wrap things up and open it for questions. So thanks, everyone.
Alex.
I have a statistics question. Are you worried about prior volume projection effects when quoting marginalized constraints?
Prior volume projection effects. So you mean like the fact that we have a 3D density model and then we're sort of, that's part of the distance constraint we get, or?
Yeah, you have the galactic prior, and if it favors certain areas of parameter space,
Yes.
then your marginalized constraint favors that part.
Yes.
The data wouldn't.
Yeah. So that comes up in a lot of contexts where we do see in cases, this comes up especially for parameters that are less well constrained by photometry or very degenerate, in particular ages and metallicities. Those tend to be more prior dominated, and you do see this sort of like pulling effect towards this. I don't have a plot here, but in the paper that was recently accepted and hasn't, so it's currently sort of going through the process of like getting published. I do have plots which show specifically the deviation from the prior when like looking at all these things. So I predict exactly what the prior would say and then what we actually see from the data. And that actually shows very clearly some of these structures like pop out. So Sagittarius is super obvious in that plot because it's just this humongous overdensity that we don't say exists. But you also see things like metallicity and velocity flows that also show up in that too. But that's a very real concern that we have. And I'd say for the catalog which we produced, which is available, that's one of the caveats that we put out, we'll want to put out on that.
I had a related question that's quick. The maser data that you compare to,
Yes.
is that like isotropically distributed? Like,
No. No,
yeah,
not
so
at all.
the comparison data, right, is in itself a biased data set, but you can assess the limitations of your priors or your models using that data?
Yeah, so for the comparison data, we can definitely say is that those are cases where our priors are definitely wrong, because we're fitting like, these star-forming regions don't necessarily follow the local properties of field stars, which is what our priors have been optimized for. But it shows that with enough, the likelihood does give enough constraints that we get good agreement. But yes, the masers are primarily all focused on star-forming regions, and so lots of this, we are using field stars to get estimates to those regions. But it still stands that those are not typical of like what stars around the galaxy are doing. Yeah.
Right.
Hi, I'm Rowan. I have an unrelated question. How well could you use this kind of data to estimate the mass of the dark matter halo around the Milky Way? Presumably, if you looked at the velocities of stars out in the halo, you'd be able to get a pretty good estimate on the velocity dispersion of them.
That's a great question. So we have actually done a little bit of this. One of the students who's not listed here, Jeff Shen, worked with me and Gwen, and then also Dennis Suritsky on trying to do exactly that, construct a hierarchical model for the mass profile of the Milky Way, get a mass estimate from that using data from the H3 survey. So it does work, yeah. There are different approaches to doing this, but when you use that particular argument, you're very sensitive to this assumed shape and properties of the distribution function. But there are ways to do it that are more non-parametric.
Yeah, how sort of can you get to like to be honest, I don't know how the dark matter mass of the Milky Way is measured. Is it a competitive way of doing it? In terms
Yeah. I don't have a plot here, but in the paper, there's a comparison to all the different ways. Jeff has color coded them by sort of like type of approach. And our constraints are very competitive, and we actually think that you can't do better than like 10 or 20%, just because systematic uncertainties are too large, especially from SMC LMC effects. So they're just very difficult to deal with without going to like full n-body simulations to account for how they impact the dark matter halo shape and things like that.
Yeah, thanks. I love your visualizations, by the way. The velocities of all that, it looks amazing.
Oh, thanks. Yeah.
Liza, did you have a question? And one last question before pizza?
Your Augustus map looked amazing.
Oh, thank you. Yeah, I thought they looked nice too.
How much dynamical stuff can you do with that? Can you like figure out how fast the spiral structure and the bar is moving and all that? Can you actually get the dynamics of the Milky Way down?
Ooh, that's a good question. So right now, we've mostly just looked at very basic things since I just kind of produced the catalog and haven't done a ton of science with it. What I can say is that catalog I don't think is going to be very good for the bar because we've cut out the galactic center. The next iteration of the catalog where we include everything from Gaia, so the full 4 pi, that one will probably be much better for that. For outer galaxy stuff, though, I think it actually could be very good. So anti-center type things, and also like sort of upper disk halo, I think would be good. You had mentioned something else as well about instead of the bar.
Oh, spiral structure, but I
So-
guess that's also in the plane.
Yeah, exactly. So anything in the plane we cut out just because there were, two times as many stars, less than B of 10 than above B of 10. So that was primarily just a time constraint. But yeah, hopefully the next iteration of this, which I hope should be out sooner than later, we'll be able to use the full sky.
All right, let's thank Josh and then tuck in.
And I think this is still being recorded.
Oh.